Hello students, today we're going to be going into the very important topic of rotational motion. Okay, so as we had discussed in the previous class, you have studied before linear motion, and that's motion that goes, just from left to right. Now we're going to go into rotational motion. So what rotational motion is as clear as it sounds. It's just motion that rotates about a fixed axis. Okay, so in order for us to begin studying rotational motion, we need to understand what our distance will be, because before it was simple to say we have a box here, it travels 5 meters to the right, so now the distance is 5 meters. However, if we have a ball or a CD that's just spinning in place, we don't have, it's not moving left or right in space, it's just staying in the same spot. So we need to define a new kind of distance, and that's going to be our rotational displacement or rotational distance. Now, how are we going to do this? First, we're going to start off by introducing something that we call a radian. Okay, so if you take a circle, okay, and let's call this the unit circle, okay? And let's say we place it on an XY axis. And the special thing about this circle is that the radius r of this circle is also going to be how we measure the distance. So what a radian is, it's what we call the distance around the circle equal to one radius. So for example, let's say this is 1 meter, and then let's say this is also 1 meter around the circle. Then we say that this is 1 radian. And the special thing about the radian as a measurement is that in a half circle, so let's say we have 1 radian there, 1 radian here, another radian here, and then part of a radian there. The special thing about the radian as a measurement is that in a half circle, so in the upper half of this circle, we have pi radians of measurement. Okay, so what that means is that if I take the radius of this circle and I put it around the edge of this circle, I'll need 3.14. I'll need about 3.14 radius distances in order to cover the first half of the circle. So that means I would need 2 pi radians for the entire circle. Okay? So, now that we have an introduction to what a radian is, let's talk about what the angle theta here is. Okay? So from trigonometry, theta is going to be equal to the distance over the radius. Okay? So where this distance s is the distance on the outside of the circle, right? Where this is the distance s and the r is the radius. Okay? So now that we have this, we can start introducing something basic. This will be our change in angular displacement. Okay? Where we have our final position minus our initial position. Okay? Where this symbol is called theta. It's a common symbol used for angles. Okay, so for example, let's say again we have a circle here, right? Let's say at t equals 0, we're over here, right? At t equals 0, and then at t equals 1, right? At t1, we're over here. So the angular displacement would be the change in this angle right here. Okay? Now, the radian is a similar unit as the meter. So same way you could just do 3 meters minus 1 meter equals 2 meters. You can do the same with radians. So 3 that's how we write radians, minus 1 radian equals 2 radians. Okay? So now that we have this, we need to apply it to our understanding of rotational kinematics. So if you remember from linear kinematics, we would have velocity equals to distance over time. Okay? So in rotational kinematics, we're going to introduce the symbol omega. It looks like a W, but it's the omega symbol, the Greek letter. So it's going to be omega is going to be equal to the change in rotational displacement over change in time. Okay? And the units for this will be radians per second. So these are the units for rotational velocity. Okay? So, now that we have this, we can do a practice problem. So, as I said before, an entire rotation around a circular motion will always be equal to 2 pi radians, okay? So I'll write that down over here. So 2 pi radian is equal to 1 revolution or rotation. Okay, so with that we can do a practice problem. Okay, so let's say we have a helicopter that the rotors spin with an angular speed of 3.2 times 10 to the second revolutions per minute. Okay. First, we need to and say we want to change this to radians per second. Okay. This is simple enough. First, we're going to let's rewrite our speed. 0.2 times 10 to the second revolutions per 1 minute. Okay. So first, let's start off by getting rid of our revolution. So as I set up here, 2 pi radians is equal to 1 revolution. So the unit that we want, we're going to keep at the top. So 2 pi radians over 1 revolution. So that's going to cancel out our revolutions. And we also want to get rid of minutes and put seconds instead. So our minutes is at the bottom. So we're going to put minutes at the top to cancel it out. So we know that in 1 minute, there is 60 seconds. So this cancels out with this. And at the end, we are left with 33.5 radians per second. So that's how fast the rotors are spinning. Okay? So now that we have this, let's say that the rotors have a radius equal to 2 meters. Okay, so the rotors are 2 meters long. And we want to find out what arc length the tip of the blade passes through in 300 seconds. Okay? So again, it's saying, let's pretend we have the rotors, right? Now let's focus on this one. It's saying in 300 seconds, how much distance does it travel around its circle? Okay? So again, we want to find out the angular displacement, right? So we want to find out what is this, okay? So from our previous equation, this one over here, we can rearrange this, right? Because we know what our omega is, we just solved for it in the last problem. It's 33.5 radians per second, and we know what the time is. This makes it easy enough to solve. So when we rearrange the equation, we have the angular displacement is equal to omega times time. So if we multiply this, we'll get 1, or here, let me be thorough. So 33.5 radians per second times 3 times 10 to the second seconds is going to be equal to 1.01 times 10 to the 4 radians. Okay, so that's how much distance it travels in 300 seconds. But we want to find out the distance around the circle, okay? We don't want it in radians, we want the actual distance. So if you remember from the beginning, we said that theta is equal to S over R. And what we're looking for is this value S right here that we call the arc length. Okay, so if we solve for this, we have S is equal to theta times R. We know what our theta is. So our theta is 1.01 times 10 to the 4 radians times 2 meters is equal to 2.02 times 10 to the 4th meters. So that's the amount of distance that the rotors cover when spinning around in 300 seconds. Okay? So, moving on, our next problem to tackle is that of acceleration or rotational acceleration. So again, similar to linear, we said that in linear, acceleration is equal to v over t. So in rotational, we're going to have the symbol alpha is equal to omega over t. Okay, and more specifically, that the change in omega over change in t. And the units for this will be radian per second squared. Well, here it was meters per second squared. Okay, so as you can see, there's a lot of similarities between the two. Okay. Now, just a quick side note. Whenever you have a what we call a rigid or a solid object spin, let's say for example we have a bike. Okay. Let's say this is like a bicycle wheel. If it's spinning, every point, if this is point A, this is point B, this is point C over here, every point on this bike is spinning with the same rotational speed and acceleration. Okay? And this holds true for all cases dealing with that deal with the rotational motion of a rigid object. Okay, so now we're going to talk about the 3 equations needed for rotational motion under a constant angular acceleration. Okay, so again, And linear motion will come up a lot because of all the similarities that exist between them, right? So in linear motion, we had the following kinematic equations. We had V is equal to V naught plus AT. We had the change in X is equal to V naught T plus 1/2 AT squared. And lastly, we had V squared is equal to V naught squared plus 2A change in X. Okay? So, in rotational, we're going to have something very similar. In rotation, we're going to have omega is equal to omega initial plus alpha t. We're going to have change in theta is equal to omega initial t plus 1/2 alpha t squared. And lastly, we're going to have omega squared is equal to omega initial squared plus 2 alpha change in theta. Okay? And these all work the same way that the linear equations work. There's nothing different between them. They all do the same thing. All right. So with that being said, we're going to head into the discussion portion of the class. If you have any questions, now's the time to ask. And yes, thank you.